We present SMASH, physics-guided reconstruction of collisions from videos. Collisions capture suspense, build anticipation, and pack drama. SMASH reconstructs in 3D an accurate, physically valid collision using laws of rigid body physics for regularization. We do not directly work with the object's geometry, but analyze the object's motion before and after collision. We can therefore reconstruct a physically plausible collision even under severe occlusion. SMASH operates in the following key stages. First, we calculate positions and orientations from the input video, and then optimize for a physically plausible best data fit. We first calculate screen space object positions automatically using a physics-guided, robust fitting method. Standard video analysis yields a set of noisy object centroid candidates. We approximate the depth by a single value for robustness, assuming roughly frontal-parallel collisions. In a ransack-based sampling approach, we either assign the centroids to the objects or reject them as outliers. As output, we store the labeled centroids, an initialization of the parabola parameters, and an approximate collision time. Using the analytic parabola positions from the previous step, we can render the pre-scanned objects and compare them to the image regions from the earlier background subtraction step. We use OpenDR to adjust the orientations and suggest top candidates to the user, who annotates in total 8 orientations, concluding our semi-automatic orientation initialization step. We are now ready to proceed with our main optimization step. The input consists of labeled screen space centroids, 8 orientations annotations, and initial parabola estimates. Starting from a frontal-parallel initialization, we then use our full physically regularized pipeline to reconstruct the collisions. We output analytic descriptions of the object's motion states, and most importantly retrieve otherwise invisible internal parameters of the objects, their relative mass, and coefficient of restitution. Please refer to the paper for details. We validate our estimates of coefficient of restitution by comparing to measurements made using the height method. The coefficient of restitution for two objects can be defined as the fraction of kinetic energy retained after collision. We validate by reconstructing 4 types of balls dropped in 12 different recordings in total. The football sequence is a good example of how our physics regularization robustly filters out false positive image regions originating from reflections or shadows. The height-based estimation method can only be applied when all kinetic energy after collision is converted back to potential energy. We performed our reconstructions fully automatically, assuming no spin, getting plausible measurements. Our method continues to consistently estimate the coefficient of restitution even when some energy is converted to kinetic energy throughout the recording. That is, the ball is spinning or it starts off spinning. We also evaluated the robustness of our method using the bullet physics engine. We performed over 2,000 experiments to evaluate robustness to simulated measurement errors in the position and orientation estimation steps. Please see the paper for further details. We also reconstructed series of real-world collisions. Note that we lack the ability to measure ground truth coefficients of restitution for pairs of objects. We therefore reconstructed 3 different collisions using the same pair of objects to evaluate the stability of our measurements. Thus, our method enables measuring the unobserved internal physical properties of objects that previously have been difficult to acquire in such uncontrolled environments. Overall, the reconstructed internal properties are reasonably stable, and the reconstruction fidelity is high, suggesting that there is a lot of unleveraged information in the motion of the objects. We next show how our algorithm performs on collision videos involving non-box objects. We present 3 sequences of varying complexity: duck elephant, helmet duck, and duck rugby. Our physics model works by inverting the impulse model. That is, we assume that the objects are perfectly rigid and the collision happens instantaneously. Qualitatively, the coefficient of restitution estimates are plausible. For example, the bike helmet gives a low estimate as it acts as a shock absorber. In contrast, the elephant and the rugby are bouncy and give high coefficient of restitution estimates, with the rugby giving the highest value. Note that our optimization does not include any explicit collision detection or resolution terms. We are looking for the best, physically plausible explanation for the observed pre- and post-collision motion of the object, allowing us to be robust to occlusions happening during the collision of complex objects. We developed a Blender plugin to help author complex, novel collision sequences using the parameter estimates from real collisions. The plugin allows the user to combine several observed collisions, time them to synchronize, or even stagger the interactions. Note that the user does not have to guess physical parameters for the objects. They are automatically estimated during reconstruction. Based on our reconstructed solutions, the new simulations behave naturally, and the objects collide as we would expect them to do from their real-world counterparts. Thank you for your attention. Code and datasets are available on the project page.